Alright, we're going to look at the graphs of uh, y is equal to a to the x, where a is greater than 0. Okay, because this is what the specification wants you to know. And then we're also going to look at y is equal to e to the x, which is a special case of this. And there's 3 different cases we have to consider. So first up, there's the case where a is greater than 0 but less than 1. And in this case, as we get positive powers of x, okay, y is going to get smaller and smaller and smaller and smaller because we're taking the power of a 0 point something. So if you think for numbers less than 1, if we were write them as a fraction, the denominator would be bigger than the numerator. So when we take powers, we just amplify this. The denominator gets even bigger, and it gets bigger much faster than the numerator. So y gets smaller and smaller. And then when we're taking negative powers of x, well, that means we're flipping over the fraction, so the opposite happens. We're going to get bigger and bigger and bigger, and of course at x equals 0 we get 1, like we do for all powers. So we start here, we get some sort of exponential growth through here, and then an exponential decrease. Alright, and then there's the case where, and this is the simplest case, where a is equal to 1. And when a is equal to 1, it doesn't matter what the power is. We just get a straight line through y equals 1. Okay? And then the final case is when we have, these xy planes still, is when we have a greater than 1. And this is just the opposite of this case here. Okay, so a's positive number greater than 1. So when we've got negative powers, if you think y equal to the a of minus x is equal to 1 over a to the x. Okay, so when we have those negative powers, as they get bigger and bigger and bigger, it gets smaller and smaller. We come up to 1, then we shoot up. So as I say, it's just the opposite of this graph. Things you need to know: the bigger the value of a we're putting in, the steeper this curve will be. Okay, and here, like the opposite, sort of the smaller you get, the more intense this growth will be. The final thing we want to look at is y is equal to e to the x, and the first question you naturally ask is what is e? Well, e is equal to 2.71 something. It's Euler's number. It can be more accurately displayed as a power series, and if you go on to do further maths, and I'm sure you'll look at, and when I say further maths, I do mean further maths and then just generic further maths study, you will see this number crop up in much more detail. But what's nice about the graph of y equals e to the x is it looks the same because e is a positive number greater than 1, so we get the same sort of shape as that graph there. Okay. But what's also nice is if we take the first derivative of e to the x, it's just equal to e to the x. So what's nice about this graph is that at any point the y value is equal to the gradient, which is a very nice property to have. Like I say, we'll see more of this function e to the x in some of the later videos. So I hope you understand this graph now, and also I hope you can appreciate how this technique here of using the analysis. So considering different values of A is a very powerful technique, not just for this, in a lot of problem solving aspects and graph sketching and stuff. So be sure to think about that sort of logic when you're doing problems. But yeah, that's it for this video. If you've got any questions, let me know down in the comments section below. Now that's it, and I hope to see you in the next one.